high-quality frequency from a central source to every node in the network, ensuring that all devices tick at the exact same rate. Here is a breakdown of the architectural layers and the mechanisms that keep them stable. 1. The hierarchical structure. SyncE architecture follows a tree-like topology to prevent timing loops and ensure a clear traceability back to a primary source. Level 1. The primary reference clock, PRC, the root of the architecture. This is usually a GPS/GNSS receiver or a cesium atomic clock. It provides the grandmaster frequency. Level 2. The core/boundary nodes. These are high-end routers that lock their internal Ethernet equipment clocks, EEC, to the PRC and distribute that frequency to multiple downstream branches. Level 3. The access/edge nodes. These are devices like cell-site routers or enterprise switches that receive the clock and provide it to end-user equipment, such as 5G base stations. 2. The physical layer mechanism. The architecture relies on the Ethernet PHY, physical layer, to transport the clock. Unlike standard Ethernet, where the clock is generated locally by each device, a SyncE node extracts the clock from the incoming bit stream of its upstream neighbor. The internal clock of the device then locks to this extracted frequency. The device then uses the synchronized frequency to encode its outgoing data on its downstream ports. 3. The control plane, ESMC and SSM. A critical part of the architecture is the Ethernet synchronization messaging channel, ESMC. Without it, a node wouldn't know if the clock it is receiving is high quality or failing. Synchronization status messages, SSM. These are heartbeat-like packets sent over the ESMC, standardized in ITU-TG.8264. Quality level, QL. Each SSM contains a QL value. For example, a clock from a PRC might have a QL of PRC, highest, while a node in holdover might send a QL of SEC, lower. Selection logic. If a node has two upstream connections, its architecture allows it to look at the SSMs from both. It will automatically lock onto the port with the highest quality level. For resiliency, holdover and protection. SyncE architecture is designed to be self-healing. 1. Redundant paths. Most architectures provide at least 2 paths to a PRC. If the primary link fails, the node detects the loss of signal or a drop in QL and switches to the secondary path. 2. Holdover mode. If all paths to a PRC are lost, the node enters holdover. It uses its internal oscillator, often an oven-controlled crystal oscillator or OCXO, to maintain the last known good frequency for as long as possible until the primary source returns. 3. Loop prevention. The architecture uses the SSM/ESMC messages to prevent timing loops, where router A locks to router B, which is inadvertently trying to lock back to router A. Summary of architectural goals. Feature architectural implementation. Traceability. Every node can trace its clock back to a G.811 PRC. Loop-free ensured by ESMC/SSM logic and manual priority settings. Stability provided by Layer 1 extraction, immune to packet congestion. Redundancy supported by dual homing and automatic clock source selection. Advantages of SyncE. Synchronous Ethernet. SyncE provides a stable, physical layer frequency reference that addresses the timing gap in standard asynchronous Ethernet. By bringing legacy-style clocking to modern packet networks, it offers several critical advantages for 2026 infrastructure. 1. Carrier-grade synchronization. SyncE transforms standard Ethernet into a synchronous medium comparable to legacy SONET/SDH. Physical layer stability. Unlike packet-based timing, NTP/PTP, SyncE derives its clock from the bit stream on the wire. This makes the synchronization immune to network congestion, packet loss, or delay variation, jitter. High precision. It meets the stringent ITU-TG.8262 standards for clock accuracy, ensuring that frequency drift is kept within parts per billion, which is a requirement for carrier-grade service level agreements, SLAs. Traceability. It supports the ESMC, Ethernet Synchronization Messaging Channel, protocol, allowing routers to automatically select the best available clock source and prevent timing loops. 2. Support for mobile networks. 5G/6G, modern cellular networks are the primary drivers for SyncE deployment. Spectral efficiency. 5G TDD, time division duplexing, requires all base stations to be perfectly synchronized. SyncE provides the stable frequency foundation needed to prevent radio interference between neighboring cells. Seamless handovers. When a user moves between towers, the handover is only successful if both towers' frequencies are aligned. SyncE ensures this alignment, reducing dropped calls and data stalls. Front haul accuracy. For Cloud RAN architectures, SyncE is essential in the front haul to synchronize remote radio units, RRUs, with centralized baseband units, BBUs. 3. Improved quality of service, QoS. While QoS usually refers to bandwidth, synchronization is a hidden layer of QoS. Reduced buffer slips. Without synchronization, a receiver's clock might run slightly faster or slower than the sender's. This causes buffer underflow or overflow, slips, which lead to audible clicks in voice calls or frame drops in video. SyncE eliminates these slips. Deterministic performance. By providing a common heartbeat, SyncE enables more predictable packet processing, which is critical for real-time applications like industrial automation and telesurgery. For seamless integration, SyncE acts as a universal translator for timing. Legacy interoperability. It allows carriers to replace old TDM, T1/E1, circuits with Ethernet while still providing the physical layer clocking that legacy equipment, like PBX systems or utility sensors, requires. PTP assistance. Hybrid mode. In 2026, the gold standard is hybrid mode. SyncE handles the frequency, speed of the clock, which allows PTP, IEEE 1588v2, to focus only on phase, time of day. This combination achieves sub-nanosecond accuracy much faster than PTP alone. 5. Cost-efficient. SyncE helps reduce both capital expenditure, CAPEX, and operational expenditure, OPEX. Hardware consolidation. By embedding synchronization into the Ethernet hardware, operators can eliminate the need for dedicated, expensive external timing boxes, bit/SU, at every site. Reduce GPS dependency. While GPS/GNSS is the ultimate clock source, it is expensive to install at every single tower and vulnerable to jamming. SyncE allows a single GPS source at a central hub to distribute that clock over existing fiber to hundreds of other sites. Lower maintenance. Because it uses standard Ethernet cabling and interfaces, it simplifies the spares inventory and reduces the specialized training required for field technicians. Summary of advantages. Aspect. SyncE benefit. Carrier-grade reliability of SONET with the speed of Ethernet. Mobile support prevents cell-to-cell interference in 5G TDD. QoS eliminates data slips and buffer errors. Integration bridges the gap between legacy TDM and modern PTP. Cost eliminates redundant timing hardware and GPS receivers. Key metrics in SyncE. In synchronous Ethernet, SyncE, performance is measured by how well a device can replicate the master clock's heartbeat across the network. These metrics are strictly defined by ITU-TG.8262 to ensure that packet networks remain as stable as legacy telecom systems. 1. Frequency accuracy. Frequency accuracy, or frequency offset, measures the difference between the actual frequency of the clock and its intended ideal frequency. The metric, usually expressed in parts per million, ppm, or parts per billion, ppb. The requirement, a SyncE primary reference clock, PRC, must have an accuracy of. A slave clock, EEC, in free-run mode must maintain an accuracy of 4.6 ppm. Why it matters. If two base stations are off by even a tiny fraction, they will drift out of sync, causing radio interference in 5G cells. 2. Jitter refers to the short-term, high-frequency variations of the clock pulses, deviations greater than or equal to 10 Hz. The metric, measured in unit intervals, UI. The cause, often caused by electronic noise, thermal changes, or internal circuitry. SyncE solution. The Ethernet PHY and the clock's phase-locked loop, PLL, act as filters to smooth out these high-speed wobbles before the signal is passed to the next device. 3. Wonder is the long-term, low-frequency variation of the clock pulses, deviations less than 10 Hz. The metric, measured using time interval error, MTIE, maximum time interval error, and TDEV, time deviation. The cause, wonder is usually caused by environmental temperature changes in the fiber optic cables or the equipment racks over hours or days. Why it matters. Wonder is much harder to filter than jitter. If wonder becomes too high, it can lead to slips in the data buffers, where a device reads a bit twice or misses it entirely. 4. Holdover is the ability of a SyncE device to maintain a stable frequency when its external reference, the master clock, is lost. The metric, measured by the frequency drift over time, example remains within 1 ppb for 24 hours. How it works. When the lock signal disappears, the device uses its internal high-quality oscillator, like an OCXO, to mimic the last known good frequency. Why it matters. Holdover provides survival time. It gives network engineers a window, usually several hours to a day, to fix a fiber cut or GPS failure before the mobile towers in that area completely lose synchronization and shut down. Summary table. SyncE metric comparison. Metric focus time scale. Primary cause frequency accuracy precision constant quality of the oscillator, PRC/EEC, jitter wobble 0.1 seconds electronic noise/PHY artifacts wonder drift 0.1 seconds temperature changes in fiber/hardware holdover survival hours/days loss of primary clock source. Applications of SyncE in 2026. Synchronous Ethernet. SyncE serves as the heartbeat for high-performance networking. While the world has moved toward packet-switched data, the physical layer stability provided by SyncE remains a mandatory requirement for industries that cannot tolerate timing drift. 1. Mobile backhaul, 5G/6G. Mobile backhaul is the most critical application for SyncE. It connects the cell-side router, CSR, at the tower to the mobile core. Frequency alignment. 5G radios use time division duplexing, TDD, where the same frequency is used for both upload and download. If towers are not perfectly synchronized, they will talk over each other, causing massive interference. Small cell density, with 5G's use of high-frequency wave, many small cells are deployed close together. SyncE ensures these cells act as a single, coordinated fabric. Foundation for PTP, in mobile backhaul, SyncE is almost always used in hybrid mode. It handles the frequency synchronization, allowing the precision time protocol, PTP, to focus on the much harder task of phase/time of day alignment. 2 Carrier Ethernet, slot-driven services. Service providers use SyncE to offer carrier-grade Ethernet services to enterprise customers, such as banks and broadcast media. Deterministic performance. By providing a synchronized clock, carriers can offer service-level agreements, SLAs, that guarantee extremely low jitter. Video broadcasting. For live 8K video contribution, any clock slip results in a dropped frame or a digital artifact. SyncE keeps the video encoders and decoders at both ends of a metropolitan network perfectly in step. Financial services. In high-frequency trading, SyncE provides the underlying frequency stability required to ensure that all trade matching engines across a city are timestamping transactions with nanosecond consistency. 3 Packet Transport Networks, PTN. PTN is a multi-service architecture designed to carry both legacy and modern traffic over a packet core. Unified timing. SyncE allows the PTN to act as a timing transparent network. It distributes the clock from the core to the edge without being affected by the volume of data traffic. Efficiency. Instead of running separate, dedicated timing cables, like bit/SU, throughout a central office, the PTN uses the existing 100G/400G fiber interfaces to carry both the data and the clock signal simultaneously. For replacement of legacy SDH/SONET, many critical infrastructure networks, power grids, railways, and utilities, are finally decommissioning their 30-year-old SDH/SONET equipment. Maintaining the clock, legacy equipment was built to expect a physical layer clock. SyncE is the only Ethernet technology that provides this, allowing these organizations to upgrade to 100G Ethernet while keeping their specialized legacy sensors and control systems operational. Circuit emulation, CES. When a legacy T1 or E1 circuit is emulated over a packet network, SyncE is used at the receiving end to reconstruct the constant bitrate signal perfectly. Without SyncE, the reconstructed voice or data would suffer from bit errors due to timing mismatch. Summary of SyncE applications. Application area. Primary driver. Key benefit: eliminates radio interference and dropped mobile backhaul 5G TDD and handover calls. Carrier Ethernet. Strict SLA/media provides deterministic, jitter-free data delivery. Simplifies infrastructure by removing dedicated packet transport network convergence timing wires. Legacy infrastructure allows legacy hardware to run on high-speed replacement modernization fiber.